I want to do an example using conservation of mechanical energy. So I have a system here of two blocks connected by a string. Block A is connected to a spring which is attached to a wall, while block B is hanging freely. And so mass of block A is 5 kilograms. The mass of block B is 10 kilograms. Our spring constant is equal to 200 newtons per meter. And we're going to say that the system is released where the spring is unstretched. And we want to know how fast is block A moving after it has fallen half a meter. What is the velocity of block A? Hold on. Let me say. All right, I want to change this here. I'm going to call my hanging block mass A. Block B is attached to the spring. Okay, so what is the velocity of A after it has fallen after 0.5 meters? All right, so let's see, what can I say about this system? So we do say it's frictionless. So what are the forces that are acting on A and B? So on A, there's gravity and the tension in the string. B, there's the normal force and gravity, as well as the spring then and the tension in the string. And so our first question is always, so do we have conservative forces? Conservative forces. And we don't have all conservative forces, gravity in the spring, but we also have the normal force on B, as well as the tension force on A and the tension force on B. These are non-conservative forces. However, are they doing any work on the system? Certainly, the normal force is doing no work on the system because the normal force is vertically up, while B, the object, is only moving horizontally. Since the normal force on B is perpendicular to the displacement of B, then the work is 0. What about the tension? So given our string model, our string has no mass and it doesn't stretch. The tension is everywhere the same. And so if the system then moves, say, some distance delta x for B, A is going to move the same distance delta x. So the tension on B, so let's say delta x is moving this way. The tension on B is pulling in the direction of the motion, and so there's going to be some work done by the tension on mass, B that's equal to the tension in the rope times the displacement, and they're in the same direction, so that's positive. Now, the tension is also going to do some work on mass A. That work is equal to the tension, which is everywhere the same, so this tension is equal to this tension, times the displacement of mass A. Now, the magnitude of the displacements, those are the same, but for A, the tension now is in the opposite direction of the displacement, so the work is negative magnitude of the tension times the magnitude of the displacement. So the net work here, work of A plus the work of B, is equal to 0. So for this system of the masses A and B, the only work being done are done by conservative forces. The non-conservative forces do not do any work on the problem, on the system, which is the masses A and B, the combined system of the masses A and B. Okay, great. So now let's look at our coordinate systems and establish our forces and the potential energies. All right. So for B, let's get a coordinate system here. So I'm going to call my 0 of my coordinate system at the equilibrium position, and I'm going to so x, positive x in off to the right. So for A, then I'm going to say I'm going to give it a coordinate system. Its 0 is going to be at its location when B is at equilibrium with the spring, and I'm going to give it a positive x down, so that if A is positive, if delta x is positive for A, then delta x is positive for B. So what does this give us for the forces then? Okay, so so for B, what forces are doing work on the system? For B, that's just the spring force. And so the spring force then, given the coordinate system of 0 at equilibrium, is negative k times x, whatever its displacement is. The force then points in the direction toward equilibrium. All right. So the other force doing work is the force of gravity on B is not doing work, since that's perpendicular to the displacement. The other force doing work is the force of gravity on A. And so that's equal to the mass of A times g, and it's positive given this coordinate system with x pointing in the down direction. Okay. So now those are the forces. Now let's look at the potential energies. So to do that, we have to come up with the zeros of potential energies. Okay. And so I'm going to go to a different color for potential energies. The first thing we have to do is establish the zeros of potential energy. I don't need to be here. Okay, so now for potential energies. Okay, so first the force of the spring. Let's establish the 0 of potential energy at the equilibrium position. So 0 at equilibrium for the for spring. And for the gravitational force at A, let's call the 0 at x is equal to 0 at the 0 of the coordinate system for mass A. So for the gravity for F sub g on A, we're going to say the potential gravity on A of x is equal to 0 is equal to 0. So what does this give us for potential energies? So our potential energy then for this spring is negative the indefinite integral of the force, so that's 1/2 kx squared. We've seen this before, plus some constant, but given this 0 at equilibrium for a spring, that's 0. So the potential due to gravity for mass A is the negative indefinite integral of that force, which is negative mass of A gx, right? So remember, given in this case, I chose as my coordinate system positive x down for mass A because I wanted it sort of in the same direction, positive x to be the same for each mass. And that's a choice. I could have had it pointed up if I wanted to. But because of that choice of coordinate system, that means my mathematical representation of my force is positive mass times g in the x direction. That gives me a potential energy function, which is negative mass of A times g times x. And again, there's no constant because I chose the 0 of the potential energy at the 0 of the coordinate system. Okay, so now I have my potential energy functions that are related to my conservative forces, the only forces that are doing work on the problem. And so now I choose 2 points of time, and then I want to add up all my energies. So my 2 points in time that I wanted to do here, so my initial is at the point of release. And at that point, it was where the spring was at equilibrium. And that's given by how I've set up my picture here. So if it's released from equilibrium, that means it was released from rest, so its kinetic energy is equal to 0. It was at equilibrium, so the spring potential energy is equal to 0. And given my choice of coordinate system, 0 at the initial position, and my choice of 0 for my potential energy, which is at that same equilibrium position, same position of mass A, my gravitational potential energy is also 0, so my total energy is 0. So the sum of all my energies will always be 0, given that energy is conserved. So that's my initial. So what happens in my final time? My final instant in time, I'm looking for what is the velocity after the system has moved half a meter. So if it's moved half a meter, we're saying it has some kinetic energy, so it's moving at this point. So its kinetic energy is 1/2 mv squared. It has some spring potential energy, and so the spring is now extended by an amount, so d is equal to 1/2 meter. So it's equal to 1/2 k d squared, the amount that the system has moved. And the gravitational, it now has gravitational energy given by the potential energy function, which is negative massive A g d. So I add all of these together, and I have 1/2 mv squared plus 1/2 kd squared minus massive A g d is equal to 0. Okay. Well, now I can plug in these values. This is 10 plus 5, right? So I skipped a step here, and I really tried not to do that. So if I look at the kinetic energy, I have the kinetic energy of two particles. I have the kinetic energy of mass A, which is 1/2 massive A v of A squared, and I have the kinetic energy of B, which is 1/2 massive B v of B squared. Okay, and so then, of course, the total kinetic energy is the sum of these two. Now, the first thing I recognize is, since they're attached on a string, which can't be stretched, the velocities of the two objects have to be the same. The speeds of the two have to be the same. And so Ka plus Kb, the kinetic energy of each object separately, is then equal to 1/2 mass A plus mass B times v squared, where this is now the speed of both masses, and if the total mass I just call m, so 1/2 mv squared now is the total kinetic energy, where m is the sum of both masses. And so that's what I had done here. And so if I want now, I can substitute in for my values. The sum of the two masses is 15, so 7.5 v squared plus this is 1/2 200. 1/2 squared is 1/4, and this is, we're going to use, g is 9.8, this is 49 then, this is 10 and 1/2, this is 25, is equal to 0, and you can plug that in your calculator. I get velocity then is 1.79 meters per second. Okay, and so again, after we have our potential energy functions given our coordinate system and the functions of our forces, and we establish where zeros of potential energy are, then I just sum up all the initial kinetic energy, all the initial energies, which this time total to 0, then sum up all the final kinetic energies, and set the initial energy equal to the final energy and use that to solve for what I wanted. So you can see one of the things that happens here is that potential, while kinetic energy cannot be negative, the potential energy can. So the initial energy was 0, and at the final energy we had some positive kinetic energy, we had some positive amount of spring energy, and a negative amount of potential gravitational energy, the sum of all of which was equal to 0.